Good morning. If you're in honors chemistry, last Friday during our Zoom class session, we created a chart like this for VSEPR. And so if you missed that session on Friday, please take a moment, pause this video, and copy down this chart, even if you don't fully understand it. And in the rest of this video, we're going to try to apply VSEPR to some specific molecules. I've added in a column from last Friday with the heading examples, and so we have specific examples of molecules that have the shape possibilities that are shown here. So let's go ahead and get into this. We're going to try to apply VSEPR to some other molecules. So in your packet, I want to move on to the page. Let's see, shapes of molecules. So this is one where we practiced some Lewis structures. And so what I want to do is focus on the Lewis structures, and we're going to apply VSEPR here. So we have valid Lewis structures for these ones. And actually for number 11, I'm not even sure. I don't remember why we skipped that one. But I want to do that one right now quickly, and that'd be a great one to start with. Okay, so for VSEPR, we need to start off with a valid Lewis structure. So carbon has 4 valence electrons, the hydrogen has 1, and the 3 chlorines have 7, each one of them. So 7, 14, 21, 22, 26 valence electrons. Okay, and so we put the carbon atom in the middle. We attach the chlorines, with single bonds, and also put the hydrogen on there. Everything's attached to the central atom. We've used 8 electrons. Okay, and so we've got 18 more electrons to put in there, and we place them as lone pairs on the atoms that need octets, and that means the chlorine atoms. Okay, so this is the Lewis structure for this molecule. So now let's apply VSEPR. Valence shell electron pairs repel. We want to identify the central atom, that's the carbon atom, and then count up the number of electron pairs around the central atom. So notice we've got 4 bonds around the carbon in the middle. So 4 effective pairs. 4 effective pairs of electrons. So let's go back and look at that chart, that table I made. 4 electron regions around the central atom. So we're in tetrahedral parent geometry. Now, there are actually 4 atoms bonded to the central atom, 3 chlorines and a hydrogen. So the actual molecule is going to be tetrahedral. It's going to have, there's 4 pairs of electrons with 4 atoms actually bonded with the central atom. 5 atoms total, but 4 atoms bonded with central atom. And so that means we've got a tetrahedral molecule. Okay, so the shape of this molecule is tetrahedral. Let's go back up here and kind of go through them one by one now. Okay, so in this molecule, it's a diatomic molecule. If you think about it, there's not really too many ways you can attach 2 atoms together, whether it's a single bond or a double bond or a triple bond. What is the arrangement of those atoms in space? That's a line, okay? If we drew them pointing upward or pointing to the side, whenever you have 2 atoms connected with some type of bond, it has to be a linear shape. So that's not even one that we've considered here in the table. The simplest molecule in the table has 3 atoms, and then 4 atoms, 5 atoms. But if you only have 2 atoms bonded together, it has to be linear. Okay, so diatomic molecules will all be linear. Okay, that's not even VSEPR, that's just like straight up logic. Let's look at the water molecule. So the water molecule, find its central atom, of course that's the oxygen atom, and then count up the number of electron regions around the central atom. We've got 2 bonding pairs and 2 lone pairs, 4 effective pairs of electrons. Okay, so we're in tetrahedral parent geometry. 4 electron regions, it's like these 4 balloons that we tied together, tetrahedral parent geometry. Bond angles of approximately 109.5 degrees. But what about the shape of the molecule? We need to find one of these shapes that has 2 lone pairs, because in the water molecule, you can see that we've got 2 lone pairs. Okay, and so this is going to be the bent scenario. Water molecules are bent molecules. Okay, bent tetrahedral parent geometry, but with 2 lone pairs. The shape of the actual molecule would be bent. And this is another way that you can draw the water molecule. Okay. Remember, it's not flat. This bond angle is not 90 degrees. It's 109.5 degrees. Okay, carbon dioxide. Find your central atom. It's the carbon. And then count up the number of electron regions around the central atom. Double bonds count as effective pairs. So we have 2 effective pairs. 2 effective pairs of electrons around the central atom. Okay, and so those 2 double bonds repel each other to the max, and we'd get a linear shape. So we could go ahead and add in carbon dioxide. It's such an important molecule, it's important to remember that it's a linear molecule. Those 2 double bonds repel each other. Okay? So linear. Those 3 atoms are in a linear arrangement. Let me rewrite that in green since I was using green. Linear. Okay. Okay, so you can't just count up the number of atoms to figure out the shape. You have to count the effective pairs of electrons around the central atom. So the water molecule has 3 atoms. Carbon dioxide also has 3 atoms, but we end up with different shapes because these 3 atoms have 4 effective pairs of electrons around the central atom, and this molecule has 2 effective pairs. Okay, ammonia, NH3. You getting the hang of this? Find your central atom and count up the number of effective pairs. 1 lone pair, 3 bonding pairs. We've got 4 effective pairs of electrons with 1 lone pair. So 4 effective pairs means we're in tetrahedral parent geometry with 1 lone pair up top, trigonal pyramidal shape. Trigonal pyramidal shape. Oop, I just jumped down. Trigonal pyramidal. Ooh, pyramidal. There. Okay, ammonia's trigonal pyramidal. So in other words, let's redraw it. 1 lone pair, and then 3 bonds down to these atoms right here. Okay, so right here, that's the nitrogen atom, and this one, and that one, those are the hydrogen atoms. So let's continue a little bit more, and then you'll get to work out the shape of 6 and 9 here in a minute. But let's do number 5. Central atom, carbon. Effective pairs around the central atom, that's 4. Tetrahedral. It's got to be tetrahedral. Tetrahedral shape. Okay, so for practice, by tomorrow, I'd like for you to complete number 6, number 9, number 7. It's not really VSEPR, but you should still be able to do number 7. And if you can do number 7, you can do number 10 and number 12. So for practice, I'd like for you to do 6, 7, 9, 10, and 12. And technically, the only time you have to use VSEPR is with number 6 and with number 9. These ones, if you were listening earlier, there's a very easy way to know what the shapes are for those ones. And we are skipping number 8 on this page. Okay, so go ahead and complete those and you'll be done for the day.